Hello, class, and welcome to Module 4. While there are no date restrictions on your modules, focus on completing this before the fifth week of class if you want to stay on a weekly schedule. In this module, I want to go over the course, learning objectives, the overview, and objectives, our reading material, chapters 6 and 7, the supplementary online resources that I want you to watch, and then the activities that we're going to go through for this particular module. So first, let's start with the learning objectives. So there are two course learning objectives for this module. CLO 3, which is balancing chemical equations, including oxidation reduction equations. And then CLO 4 is perform calculations using the mole concept, molarity, and chemical stoichiometry. In this module, we will discuss the mole concept and apply it to the idea of limiting chemical reactants and theoretical yields. This will allow us to gain a solid understanding of the mechanics of balancing different kinds of chemical equations. Our objectives: understand how to calculate the number of moles in a given mass of a substance or the mass corresponding to a given number of moles. Given the formula of reactants and products, we want to write balanced chemical equations for the reaction. We want to write a balanced net ionic equation for a reaction between aqueous solutions of two ionic compounds. We want to write appropriate chemical conversion factors to calculate the masses of all components of a chemical reaction when the mass of any single component is specified in any system of units. When the masses of two or more reactants are specified, identify the limiting reactant and find the masses of all components present when the reaction is complete, including the calculation of theoretical yield. And so we're going to look at our chapters. So we have chapter 6. And when you click on chapter 6, it's going to automatically pop up at the intro of chapter 6. But there are 4 sections in this chapter. And so it gives you the introduction, talking about this beautiful swimming pool. And then it goes on to formula mass. And when we're talking about formula mass, now we're looking at those atomic mass numbers that are in the periodic table. And for the purpose of calculations, we went around to 2 places after the decimal for our different masses. And remember, these numbers are found as the bottom number in your periodic table. Generally, this is 1.01, so you can use 1.01 for your calculations that you will be doing for your assignments. But if we look at this, if we have 1 carbon, 1 hydrogen, and 3 chlorine, okay, and we're looking at this formula right here. And so for this formula, the one that I'm highlighting here, all right, so for this one that I created this highlight, we have 1 carbon. So if you don't have a subscript, remember it's understood to be one of them. Hydrogen again has 1, and then the chlorine has a 3 for the subscript, so there are 3 of them. So you're going to take each of these numbers, multiply it by the mass we see in the periodic table, and then we get these numbers right here. What we want to do now is add all these numbers up and we get 119.37. We know that we only do 2 decimal places based on the rules of significant figures that we've studied previously. So that's going to be the molecular mass for that compound. Now we're going to look at another example, which is C9H8O4. Okay, for this one, we have 9 carbon, 8 hydrogen, and 4 oxygen. We still have 12.01 for our mass for carbon, 1.008 for hydrogen, and 16.00. So for oxygen, it's like 15.999. I'm looking at my periodic table on the wall. So it's a 16.00. We're going to round it up to that. So again, we're going to multiply our the number of atoms by our mass. Okay, for carbon, we get 108.09. For hydrogen, 8.064. And for oxygen, 64.00. Then remember, we're going to add all those numbers up. We get 180.15. So that is how you calculate your molecular mass for a compound. And so go through, there's a couple of more examples that you can look at so that you can get practice in calculating your molecular mass. The next thing we're going to look at is percent composition. So we want to know what percentage of a particular element is in a particular compound. And so if we're looking at percent hydrogen, it's the mass of hydrogen over the mass of the compound times 100. That percent just tells us that's what the unit is going to be for our final answer. It doesn't mean we're converting anything to decimals at this point. All right, so let's look at, and it's the same for our percent carbon. The mass of carbon over the mass of the compound times 100%. So we're going to look at an example. We have a 10.0 gram sample, 2.5 grams of hydrogen, 7.5 grams of carbon. So we're going to take our 2.5 grams of hydrogen over 10.0 grams of the compound, multiply it by 100, we get 25%. Since it's just two elements in this particular compound, you could simply take 100 minus 25% to give these 75%, or you can do the calculation where we take the 7.5 grams of carbon over 10.0 grams of the compound times 100, and we get 75%. All right, and so there are some more examples here. So go through and look at these examples as well so that you can get more practice. Now, what if you didn't have the masses of the compounds, but you had the molecular mass for the compound and then the atomic mass for your elements? We can still look at our percent of the different elements in the compound. So for this example, we are looking at NH3. Okay. So for NH3, we know we have one atom of nitrogen, three atoms of hydrogen. And so one atom of nitrogen is going to give us 14.01, okay, AMUs. We have three of our hydrogen. And so if we're looking at that calculation, then it's 3 times 1.008 AMUs times is equal to 3.024. Now, AMU represents atomic mass unit. It's the same thing as if we were looking at grams per mole, okay? And so we want to add those two numbers up to give us our mass of the compound. And so we have 14.01 plus 3.024, and those are AMUs, is equal to 17.03 AMUs. So now we're able to look at the percentage of nitrogen and the percentage of hydrogen in that compound. So percent of nitrogen is 14.01, which we had up here. And we're dividing it by 17.03, which we calculated up here, and multiply it by 100. Don't forget to multiply it by 100. So you get 82.27%. We can do the same thing for hydrogen. 3.024 AMUs over 17.03 AMUs times 100, and we get 17.76. Just like we looked at previously with the carbon and the hydrogen, if you just have two elements here, you can always say 100 minus the 82.27, and we will get 17.76. Okay. And so go through, there's a couple examples here that you want to go through so that you can get good practice. All right. And so what if we want to go from grams to moles? Okay. Grams to moles. Now, When we're going from grams to moles, this is going to help us when we're determining the empirical formula. We're going to start off with 1.71 grams of carbon and 0.287 grams of hydrogen. Okay, that's what we're starting with in this problem. We want to convert both of these to moles, all right? So we're going to multiply by our 1 mole of carbon over 12.01 grams of carbon. Remember, that's from the periodic table. And then 1 mole of hydrogen over 1.008 grams of hydrogen. All right. Our grams are going to cancel out, and we're left with moles. So we get 0.142 moles of carbon and 0.284 moles of hydrogen. And so we're going to look at these numbers. We want to determine which one is the smaller of the two numbers. You're right. It's the 0.142 moles of carbon. Woo woo. All right. Uh-oh. I'm just trying to highlight this. Got excited. Nope, nope, nope. All right, let's try it this way. No. Okay, so it's not wanting to. All right, so we know that it's 0.142. Now, when we're trying to figure out the empirical formula, you want to divide the both of the number of moles by the smallest, okay? And so we're going to set up our formula. We're going to start with carbon because it has the lowest number. So we're going to put 0.142 over 0.142. And then for hydrogen, 0.284 over 0.142. And we get that these two cancel out, so we're left with 1. These two, when we divide them, we get 2. So CH2 would be the empirical formula, okay? This is how you do it for each of your compounds that you're looking for the empirical formula. So let's look at this example that they've set up. So if it was determined that chlorine is 0.150 and oxygen is 0.525, remember you're listing the element that has the lowest number first, all right? We're going to divide both numbers by the smallest number. And so we got 0.150 over 0.150, that is naturally 1. 0.525 over 0.150 is 3.5, okay? And so that is your empirical formula. This nice flow chart here gives you the step-by-step process that we just did in this example, all right? And so try these and see if you get the answers that they got, all right? So one thing I do want to mention on this one, which is true for the one we got up here with the decimal, all right? So the decimal, if you have a decimal, okay, you want to multiply it by a whole number so that these subscripts are whole numbers, all right? And so this one, we're multiplying it by 2. And so we have Fe2 and then O3. So practice those, all right? And then there's some other examples it gives where we can look at percentages and we're looking at molecular formulas. So this one I want to go through molecular formulas. The rest were just extra practice on things that I've already talked about. But if we're looking at a molecular formula, so say you have your empirical formula and you want now your molecular formula. The molecular or molar mass will be given to you in the problem. The empirical formula mass you can find based on the empirical formula, all right? And we know how to calculate masses. We're going to divide those two masses and you're going to get a value that you are going to multiply each of your subscripts by to get your molecular formula. So let's try one together. So it says in the problem that we have 180 AMUs. That's our molecular mass. 30 AMUs is our empirical formula mass, all right? So we're going to divide those two numbers. We get 6 formula units. So our empirical formula is CH2O. So CH2O we are going to multiply all your subscripts by 6. So when we do that, we get C6H12O6. So that will be your molecular formula. So the first one is empirical, the second one is molecular. All right. And then there's some examples here so that you can practice that as well. The next thing we look at is molarity. So molarity has this wonderful equation. Make sure you know this equation, all right? And so molarity is given by the symbol capital M, and it represents the moles of solute over the liters of solution. And so if we look at this example, we have 355 milliliters of a soft drink, and it contains 0.133 moles of sucrose. That's our table sugar. And then what is the molar concentration of the sucrose? So remember, it's the moles of solute, which is given here. All right. Moles of sucrose, that is our solute, okay? Solute is the substance that's being dissolved in the liquid, okay? And then we need liters of solution, but we're given milliliters, all right? So our milliliters, we need to convert to liters. And so it's done here. So we're going to multiply it by 1 liter over 1,000 milliliters. And then when we do the division here, we get 0.375 molar. All right. And then it gives you practice problems that you can work on so that you can be proficient in your calculations of molarity. And it gives you a bunch of different examples. One other equation was a couple of them, but they're similar. Okay, we have this one and we have that one. All right. So this is molarity times liters is equal to molarity times liters. Concentration times volume is equal to concentration by times volume. Same thing. What we're doing is if you are given two volumes and a molarity, you're trying to find the other molarity, or say you're given two molarities, one volume, and you're trying to find the other volume, you're going to use these equations, all right? And so if you look at this, when we are trying to solve, you may need to rearrange the equation to solve for what you need. And so we have 0.850 liters of a 5.00 molar solution of copper nitrate. And then we want to, and it's actually copper 2 nitrate, but anyway, it is diluted to a volume of 1.80 liters. We want to know what is that new molarity. Excuse me. The first volume and molarity listed would be your concentration 1, V1 or M1, L1, depending on which equation. The equations are the same, so it doesn't matter. And then this is your second volume. So we're looking for the second concentration. To solve for the second concentration, we want to divide both sides by volume 2, and we end up with this equation. That's going to highlight them both. All right. So this is how you'll rearrange equations based on what you're looking to solve for. So practice that. And there's some extra examples of practice as well. And then the last section is on other units of solution concentration. So we have mass percent. And so look through the examples for mass percent. Those are pretty straightforward. Okay, they're pretty straightforward. And this is a flow chart to help you if you are looking from going from milliliters or volume of a solution to the mass of the solution to the mass of another substance. Okay, and so go through that. Then we have volume percent, and then we have mass and volume percent. Then we have parts per million, parts per billion, or ppm, ppb. All right, and then there's examples of those. And so this gives you, in this chapter, this gives you a lot of practice. I would strongly suggest that you go through and do the practice so that you'll be prepared for the homework assignment for this particular module. Now in chapter 7, I'm going to delete some of these extra things up here. All right, so chapter 7, we're looking at writing and balancing chemical equations, classifying chemical reactions, reaction stoichiometry, reaction yields, and quantitative chemical analysis. So there's quite a bit in this particular chapter. And so we're going to go through, I want to go through with you writing and balancing chemical equations. This is a step-by-step process of what you're doing. And so you can go through that, but I want to give you an example. Let's go through. Okay, let's look at this first example. So the first thing you want to do is first determine if your reaction is balanced or not. And actually, I want to show you one up here. I'm going to show you this one. Okay, so that you can see one that is balanced. So if we look at that, we want to determine how many atoms of each element you have on the reactant side, which is the left side of the arrow, and the product side, which is the right side of the arrow. So for carbon, we have one carbon. It doesn't have it has a subscript of 1, so we have 1. For hydrogen, we have 4 times, so we have 4 basically. All right, so we have 4. For oxygen, we have a coefficient of 2 and a subscript of 2. So we want to multiply the two numbers and we get 4. Okay. Coefficients are the numbers that are in front of your substance in the reaction. Okay. And so if there's no number written, it's understood to be 1. So if we look at the product side, we have a coefficient of 1 for carbon and a subscript of 1. So we get 1 carbon. We have a coefficient of 1 and a subscript of 2 for oxygen. So 1 times 2 is going to be 2. But oxygen is in 2 places. So on here, we have a coefficient of 2, a subscript of 1. So 2 times 1. If we add them together, we get 4. For hydrogen, a coefficient of 2, a subscript of 2. We're going to multiply the numbers and we get 4. So now we compare to see if it's balanced. We got 1 for the reactant side, 1 for the product side. They're equal, so yes. 4 on the reactant side, 4 on the product side. They're equal, so yes. 4 on the reactant side, 4 on the product side. They're equal, so yes. If all of the elements are equal on both sides of the reaction, then we say the equation itself is balanced, okay? So let's look at one that is not balanced. And so if we look at hydrogen, coefficient of 1, subscript of 2, so there's 2. For oxygens, coefficient of 1, subscript of 1, so there's 1. Now on the product side, for hydrogen, coefficient of 1, subscript of 2, so there's 2. For oxygen, coefficient of 1, subscript of 2, so there's 2. So now we want to compare the reactant side to the product side. On the reactant side, there's 2 hydrogen. Product side, there's also 2. So the hydrogen's balanced. On the reactant side for oxygen, it's 1. Product side is 2. So 1 is not equal to 2, so it's not balanced. So if one element is unbalanced in the reaction, the whole equation is unbalanced, okay? So now we want to balance it. We want to add coefficients only. You never add subscripts, okay? Because the subscripts tell you what compound it is or what substance it is. You're only going to add coefficients, so those are numbers in front. And so our oxygen is what's not balanced. So there's 2 on the product side, but there's only 1 on the reactant side. So we're going to add a coefficient of 2 in front of H2O. We can never split a compound to add a coefficient. We always add it at the beginning. And so we put 2 in front of H2O, and then we do a recount, okay? And so 2 in front of H2O gives us now 4 hydrogen on the reactant side. We still just have the 2 on the product side. But now we have 2 oxygen on the reactant side, 2 oxygen on the product side. So now our oxygen's balanced, but our hydrogen's not balanced. So this equation is still unbalanced. So now we have to balance the hydrogen. So we have 4 hydrogen on the reactant side, only 2 on the product side. So we need 2 more on the product side. So we put a coefficient of 2 in front of H2. Because we didn't add the coefficient in front of oxygen, it doesn't change oxygen. It only changes the hydrogen. The 2 in front of H2O changes everything in the compound, okay? But now our hydrogen's balanced, our oxygen's balanced. So this is our balanced equation, all right? So let's look at another example so that you'll be able to practice these on your own. So if we look at this equation, we have N2 plus O2 produces N2O5. It is unbalanced, so let's see what is not balanced. So our nitrogen, we have 2 on the reactant side, we have 2 on the product side, so that is balanced. We have 2 oxygen on the reactant side, 5 oxygen on the product side, so that's not balanced, okay? So we want to balance it. So our oxygen on the reactant side is what's lacking, okay? So we have 2 here, but we need it to be 5, okay? Or we need 5 to be 2, but what we're going to do, because there's a 2 and a 5, if it was 2 even numbers, it would make it nice, like we looked at previously with our hydrogen and oxygen. But because we have an even number and an odd number, what we're going to do is we are going to multiply the 2 numbers to give us 10. And 10 is our least common multiple between those 2 numbers. And so to get 10 on the reactant side, we're going to put a coefficient of 5. So 5 times 2 is going to give us 10. On the product side, we're going to put a 2. So 2 times 5 is going to be 10. But remember, putting that 2 in front of the compound not only changes the oxygen, but also the nitrogen. So now nitrogen is 4. So we need to do something with the nitrogen on the reactant side. And we're going to put a 2 there. So now we have 4. So now our nitrogen balances and our oxygen balances. So the equation is balanced, right? So I strongly suggest going through all of these different practice problems on your own and making sure that you understand how to balance equations. It's going to become very important that you know how to balance them, all right? The next thing that I want to show you, and I kind of went through a little too fast. Okay, is our ionic reactions. So with our ionic reactions, we have what is known as our molecular equation, our complete ionic equation, and our net ionic equation. And you need to know how to do each of these different equations, all right? So let's look at it. So our molecular equation is this one right here, okay? Where it shows everything. Our reactants, our products, it's balanced because we know how to balance equations now. But what we want to do is we want our complete ionic equation from that. And so what we're looking for is our substances that have AQ. Okay, so we have 3 substances that have AQ. Each of those are considered to be dissolved in water. That's what the AQ means. It's dissolved in water. It's an aqueous solution, okay? Each of these can be separated into ions because once it's dissolved in water, an ionic compound becomes simply ions. You cannot do that for a solid, just the ones that have AQ. So let's look at what this looks like when we're separating into its ions, all right? So CaCl2 aqueous becomes Ca2 plus aqueous. And these charges, okay, are based on what we found in the periodic table. And we looked at this in the previous module. But if you don't remember, please refresh your memory on what the charges are and based on where it's located in the periodic table. So just to refresh your memory, Ca is in group 2A, so it has a +2 charge. Cl has a -1 charge. You don't have to put the 1, okay? Ag is automatically plus, and it doesn't depend upon where it's located. NO3 is a polyatomic ion and it has a negative charge. And we already talked about all these others. So let's look at it. So Ca +2 or 2 plus, chlorine has a subscript of 2. In the ionic equation, it becomes a coefficient, all right? So the subscripts become coefficients in the ionic equation with the exception of polyatomic ions. Polyatomic ions, they stay the same, okay? So 2Cl minus, and don't forget to put those aqueous symbols, plus 2Ag plus, it has a coefficient, you keep it. 2Ag plus aqueous plus 2NO3 minus. Remember, this is a polyatomic ion, so you leave the subscript where it is. Now it produces Ca2 plus aqueous plus 2NO3 minus. The subscript outside of the parentheses becomes the coefficient, okay? Because that's what lets you know that that is a subscript for the entire compound, all right? The NO3 you keep intact, but that 2 on the outside becomes the coefficient, so 2NO3 minus aqueous. Plus the solid, you keep it as it is, all right? So that is your complete ionic equation. Now we want to do the net ionic equation. To do that, we have to get rid of what we call spectator ions, okay? Spectator ions. So if we think about spectators, if you're at a sporting event, okay, and you're looking at the spectators are those people sitting on the sidelines. So if it is a football game, you go to a football game, everyone in the stands are spectators. They are watching the game and they might act like they're participating in the game because they're enthusiastic and trying to get their team to win and get the points and run and dodge, all of that good stuff. But they are not actually taking part in the game. Those are spectators. The same thing in this equation. There are ions that are floating around in solution. They are not part of what is going to form the solid. They're just floating around watching the reaction take place. So we want to get rid of those. The spectators are those ions that are ion on the reactant side as well as the product side. So calcium 2 plus aqueous is calcium 2 plus aqueous on the reactant side and the product side. It's a spectator. We want to cross it out. Chlorine 2 chlorine minus is aqueous here, but it's a solid here, so we want to keep that. 2Ag plus aqueous is aqueous here, but solid here. We want to keep that. 2NO3 minus aqueous is 2NO3 minus aqueous on the product side and the reactant side. So that's a spectator. So now we want to write down what is left. So we have 2Cl minus aqueous plus 2Ag plus aqueous produces 2AgCl solid. That is your net ionic equation, okay? Because they each have a coefficient of 2, we can reduce those so that we have our final answer of Cl minus aqueous plus Ag plus aqueous produces AgCl solid, okay? And then there's some examples that you can practice. Strongly suggest that you practice them, all right? So next we're going to look at classifying chemical reactions. This information, you can just go through and read it. Very important because you will be tested on identifying different types of reactions, okay? It goes through a lot of great information about writing equations for acid-base reactions and looking at different types, oxidation reduction reactions, and so forth. If you have questions, though, as you're going through these are straightforward, but if you have questions, let me know. All right. And then reaction stoichiometry. Make sure you go through those as well. It's going to show you what those coefficients represent and then how you can do calculations. Okay, these different flowcharts will be very helpful when you're doing calculations with stoichiometry. And then reaction yields, we're looking at limiting reactants. Okay, so go through those equations. All right. And then quantitative chemical analysis. This is our titrations, okay? And then looking at molarity calculations with titrations. And we'll do titrations again in Module 8 when we're looking at acids and bases. And so make sure that you understand this because you will see it again, all right? So that is Chapter 7. And so I didn't So if you need help, some more help with going through those different calculations, please reach out to me. Let me know. If you need me to do another video for just calculations, let me know. All right. So then there are these supplemental videos that are very helpful. I strongly suggest that you do go through each of these videos because they're going to help you with the naming, with the calculations, limiting reactant, percent yield, how to find the limiting reactant. And these are all awesome videos. So definitely strongly suggest that you do go through them. Okay. And let me know if you have any questions as you're going through those. So I want to go to modules on this one. All right, so the next thing is our module for activity. We're looking at the limiting reactant essay. And so in this essay, you want to give the definition of limiting in your own words. You want to give me a chemical definition of limiting reactant, two examples from your daily life of how you can use the word or the term limiting. And these are non-chemical examples, okay? Something um, that you experience in your daily life. They gave an example in the text about making cheese sandwiches and how one of the components or the ingredients for making that cheese sandwich was limiting. So you're going to give examples similar to that, okay, about your daily life. But be creative, whatever examples you want to do. Now you want to give a chemical example of a limiting reactant and the explanation of what it means for that reaction. You want to give references in APA form, okay? And so if you're using a dictionary or your textbook, then you want to make sure you cite it, all right? And so if you don't know what the APA format is, you can also always Google APA format for this particular book or this dictionary, and it'll give you the APA for that. So make sure that you are referencing where you got your information from. If you used for your definition and your example. If they both came from the textbook, that's perfect. You just need one reference. But if you got the definition from one place and the example from another, then make sure you have two references, okay? But you need at least one reference. This essay must be in paragraph form, use the proper grammar, punctuation, and sentence structure, all right? And so this short essay, 150 words or more. All right? The next thing is a quiz. Let me go back down to module 4 so I can show you. Okay, so you have a quiz, all right? The quizzes for each of your modules pretty much they set up the same way, all right? The next thing is the lab assessment. Our lab assessment is on balancing chemical equations. Nope, that's not what I want to show you. All right, let me close that and then bring it up. There we go. All right. So there's two files that you want to use. The first one gives you the instructions or gives you examples. The second one is the worksheet that you're going to fill out. And so the first one, let me go through that. All right. And so you're working alone. You're going to ask me questions if you have any. And then once you've done the assignment, you're going to upload it to your Dropbox. But this one gives you some introductions. We looked at an examples of balancing equations, but this gives you the why you're balancing equations, a little bit of the history, and then it goes through some examples. It gives you step-by-step examples that you can practice, and it gives you the answers of those. But just to give you a few examples of what you're looking at. Then you actually have your assignment. The assignment is what you are going to submit, all right? And so for here, it asks you questions about counting the atoms for each, some questions about what the arrow represents, the reactants, the products, moles, conversion. It gives you a lot of different questions based on balancing equations. And so go through this, and then it gives you a chance to balance equations, all right? And so if you have questions, make sure that you ask before you submit this, all right? So let's go back to the module. So that is it for module 4, okay? A lot of fun stuff packed into this module, so enjoy it. If you have questions, please reach out to me and let me know, and I will see you in module 5. Have a great day.